Did you ever wonder if you could have water colder than ice? Well, you can. Water normally freezes at 32 degrees Fahrenheit, 0 degrees Celsius.
And 273 Kelvin!
However, water can stay liquid at well below these points. We call this the supercooling of liquids.
Supercooled liquids are liquids that are below their normal freezing point, the point at which they would turn into solids, but they're still liquid. Now, the easiest way to do this is to exert extra pressure on it, like keeping it in a closed bottle.
We use the word cold, but by this, we mean near or below 0 degrees Celsius.
These are our two pops. As you can see, there's no ice in them yet. One has bubbles as I shook it to increase the pressure, and the other one doesn't. Can you feel it, Kyle? Is it cold?
It is a very cold bottle.
Well, we don't have a thermometer, so I can't tell you how cold. If I twist off the cap, nothing happens.
Okay.
I'm gonna twist it back on, I'm gonna shake it. See, there's already ice starting to form just from the shaking. And as you can see, there's a lot more ice as the bubbles go. And that will keep on going. And as you see, there's ice actually forming off the top of the foam. And we'll squeeze a little bit more ice out of there.
How cold it is.
And this one, it's negative 8
Fahrenheit.
It was colder. I don't know if this is frozen, it looks like it, but bubbles up here, as you can see, are frozen, and it looks like down here is frozen. But we're going to see what happens before that. And it looks like, again,
so there's definitely liquid
like
in there.
Thawing.
And as it comes out, there's ice on the top.
And as you can see all through here, this is being frozen almost instantly.
You can also see that Neil is not applying any pressure on it at all. It is all coming out of its own free will. It is very cold.
What are you doing?
Pour it out into the bucket.
Project.
Super cooling liquids.
Except this is mud, and it is really cold.
Alright, try pouring it out into the thing. Physics. Okay.
Yeah.
So we're definitely getting frozen parts out. It's basically an instant slushy.
It's a good slushy. Now I'm gonna start first one.
So yeah, pressure on liquids as they freeze will allow them to stay liquid.
As long as they have water in them. You have to have water in them, a certain amount of water.
True, true. They will stay liquid under their normal freezing point, which is basically what was happening there and in the previous one.
And this is mainly because water is annoying and does not want to follow the normal rules.
It's true, it doesn't.
Like oxygen.
Recreate this experiment at home. Take a new unopened bottle of pop, preferably plastic or glass, because metal can explode and you don't want that. Stick it in a place that is at or below 32 degrees Fahrenheit for about 2 to 3 hours. Take it out and then shake it up. For best results, we find that opening it up helps to make it freeze throughout. There we go, ice. That's one. It's Mountain Dew. Dr. Pepper. Very much liquid. Ice.
Okay, we're good.
It might be solid. It's pretty damn solid to me.
Dang.
It actually started to form most of them.
Oh, where's its thermometer?
Here, this one. I'm not working.
Oh, sorry.
You're gonna have to take it out of the case too.
Kyle, shut up. That's about 30. I wonder how it stayed above 30.
Alright, we'll be right back. Negative 11 degrees Fahrenheit for 2 hours. It just went down to 37 point something degrees Fahrenheit. The water didn't supercool in this experiment because we didn't leave it in the freezer long enough.
The problem was when water freezes, it's an exothermic process, which means the kinetic energy must be released into the system, which must be removed when water freezes. But as water freezes, it acts as an insulator. So the more water that freezes, the more it insulates, which means in turn the water will take longer to freeze.